Welcome to this explainer. If you're a BMRI student just stepping into the incredible world of diagnostic imaging, understanding how we actually capture these images is absolutely foundational. Today, we're going to trace that massive evolution, literally from the chemical-smelling, pitch-black darkrooms of the past, all the way to the sleek, solid-state digital flat panels we use today. It's really a story of ingenious physics and an unrelenting quest to see inside the human body more clearly and more safely.
I mean, just think about that for a second. How did we go from technicians standing around in pitch-black chemical darkrooms waiting for physical film to develop, to doctors getting instant digital diagnostics on a high-def monitor the literal second an exposure is made? Well, that massive technological leap definitely didn't happen overnight. It was built layer by layer, breakthrough by breakthrough.
Okay, let's dive into this. Here's our roadmap. First, capturing light with intensifying screens. Then chemistry in the darkroom, followed by going digital with CR and DR. After that, we'll look at real-time vision and fluoroscopy, specialized imaging for mammography, and wrap up with our essential key takeaways.
Part 1. Capturing light, intensifying screens. So in the early days of radiography, exposing film directly to X-rays was just terribly inefficient. The silver halide crystals in traditional film are actually way more sensitive to visible light than they are to X-rays. That meant the patient had to absorb a dangerously high dose of radiation just to get a usable image. The brilliant solution to this? The intensifying screen. Instead of using X-rays to expose the film, we use X-rays to light up a screen, and that light exposes the film. By using sheets coated with rare earth phosphor crystals, we achieved a staggering 50 to 100 times reduction in patient dose. You expose the patient to a fraction of the radiation, but you still get the exact same image density. Absolutely brilliant.
Now, the secret sauce making this possible is a physical process called fluorescence. When X-ray photons strike these rare earth phosphor crystals, the crystals absorb that invisible, high-energy X-ray and immediately emit a flash of visible light. So in those legacy cassette systems, the radiographic film, which is sandwiched tightly against the screen, is actually being exposed by this fluorescent light, not the primary X-ray beam itself.
But, physics always demands a trade-off, right? To get more speed and lower the patient dose even further, you'd use thicker screens with larger crystals. The catch? When a crystal deep inside a thick screen flashes, that light spreads out laterally before it even reaches the film, and that light spread essentially blurs the image. So, there's this constant push and pull where increasing patient safety inherently degrades your spatial resolution.
Let's move on to Part 2. Chemistry in the darkroom.
Okay, once that film was exposed, we completely transitioned from the physics of light capture over to the wet, methodical world of processing. We're stepping into a light-tight darkroom lit only by red or amber safe lights that wouldn't fog up the diagnostic image. Developing this film was quite literally a manual labor of chemistry. First, a developer chemical reduces the exposed silver bromide crystals into black metallic silver, which amplifies the invisible latent image by a factor of roughly 100 million. Crazy, right? Then, after a quick rinse, the fixer chemical steps in to strip away all the unexposed crystals so the image doesn't just turn completely black later on. Finally, it gets a thorough wash and dry.
Now, doing all of this by hand in open chemical tanks took several minutes per film. Plus, it was highly prone to human error. Enter automatic film processing systems. These machines completely revolutionized the workflow bottleneck by using continuous roller transport to pull the film through perfectly temperature-controlled chemical baths. This cut development time down from several minutes to an incredible 90 seconds. On a busy hospital floor, this leap meant much faster diagnoses and significantly better patient throughput.
Section 3. Going digital with CR and DR.
As amazing as that was, even a 90-second chemical bath couldn't compete with the demands of modern medicine forever. We eventually arrived at a massive paradigm shift, trading wet chemicals for solid-state data. The first bridge over to this digital world was computed radiography, or CR. Instead of traditional film, CR uses photostimulable phosphor plates, usually made of barium fluorohalide. When X-rays hit this plate, the latent image is stored as excited trapped electrons. You then take the cassette, pop it into a reader, and a finely tuned laser scans the plate. That laser energy stimulates those trapped electrons to release visible light, a process called photostimulated luminescence, and that light is digitally captured.
Now, what's really interesting here is the jump in workflow. With CR, you still kept the old two-step process, meaning you still had to physically carry a cassette to a reader. But modern DR, or direct radiography, just throws the cassette away entirely. By using flat panel detectors wired straight into the system, DR gives us immediate, real-time image availability, drastically better dose efficiency, and remarkably lower noise. It was a total game changer.
Drilling down a bit into those flat panel DR detectors, they basically come in two distinct flavors. Indirect conversion first uses a scintillator, like cesium iodide, to convert X-rays into light, which is then turned into an electrical signal by an amorphous silicon array. Direct conversion, on the other hand, skips that light step entirely. It uses amorphous selenium to convert the incoming X-rays straight into an electrical charge, offering incredibly sharp resolution.
Part 4. Real-time vision, fluoroscopy.
Up until now, we've really only talked about static images, snapshots in time. But what if a physician needs to actually watch a patient swallow or guide a catheter through a beating heart? For that, we need moving pictures. We need fluoroscopy. For decades, fluoroscopy relied on the image intensifier tube. This was a massive, bulky vacuum tube that converted X-rays to light, then to electrons, and back to light again. Today, just like standard X-rays, fluoroscopy has shifted to flat panel detectors. These modern panels have completely replaced those old tubes in angio suites. Because they offer flawless image uniformity, they totally eliminate weird geometric warping like pincushion distortion, and most importantly, they provide vastly superior dose performance for the patient.
Section 5. Specialized Imaging, Mammography.
Next, we turn to what might be the ultimate imaging challenge. When you X-ray a chest, you have this high natural contrast between the air in the lungs and the solid calcium in the ribs. But a breast consists almost entirely of soft tissue, glands, fat, connective tissue, which all have near identical densities. Finding a tiny tumor there is literally like looking for a ghost in a fog. So the crucial point is how we manipulate physics to solve this. Mammography uses uniquely low energies, specifically right between 25 and 35 kVp. Lowering the kVp dramatically increases the photoelectric effect. This low energy means that tiny differences in the atomic makeup of soft tissue translate into high-contrast visual differences on the image, making those subtle, life-threatening tumors suddenly visible.
To achieve that perfect, low-energy beam, mammography uses highly specialized equipment. Your standard tungsten X-ray tubes just won't work here. Instead, we use molybdenum or rhodium anodes to produce optimal characteristic radiation, right at 17 to 19 keV. They also feature extremely small focal spots, as tiny as 0.1 millimeters, to catch microscopic microcalcifications. And yes, they utilize compression paddles. While they might be uncomfortable, they are absolutely vital. They thin the tissue, drastically reduce the radiation dose, and separate overlapping structures, so absolutely nothing hides in the shadows.
Let's move to our final section, essential key takeaways.
Let's bring this all together and see how this builds into the complete picture of modern radiodiagnosis that BMRIT students really need to master. We started with intensifying screens acting as the ultimate patient safety mechanism, dropping radiation doses by a factor of up to 100. We relied on the absolute precision of darkroom chemistry with developers and fixers. Then we witnessed the CR revolution, using laser-scanned plates to bring those images onto computer screens. That paved the way for DR flat panels, bringing us true real-time cassetteless efficiency. And finally, fluoroscopy mirrored this exact leap, trading bulky intensifiers for crystal-clear, uniform flat panels.
From chemical baths to trapped electrons to solid-state digital receptors, the drive has always been exactly the same: clear, faster, safer. But as we sit here fully entrenched in the digital age, with pixel-perfect flat panels instantly sending data to servers, the hardware evolution feels nearly complete. So, I leave you with this final thought. As we transition fully into these flat panel digital spaces, how exactly will artificial intelligence write the next chapter of this imaging evolution? Thank you for joining me on this explainer today, and stay endlessly curious.